an opportunity for you to become more comfortable with these. So, some of these will be as simple still as direct evaluation. And I know it's easy to overlook direct evaluation because a lot of times it doesn't work, but sometimes it does. Like in number 1, if you just plug in 0, you get 0. We're not going to get through the whole packet, so I just kind of went to ones that I thought were worth talking about. Number 4, I want you to jump to. What are your thoughts on number 4? Brandon? Good. So, well, flip that order. Using your Pythagorean identity here. Sine squared, because sine squared plus cosine squared equals 1. Sine squared can be replaced with 1 minus cosine squared. And the benefit of that is that that's the difference of perfect squares that can be factored. And the benefit of factoring is now seeing that 1 minus cosine theta and cosine theta minus 1 can be reduced to -1. So this function has been simplified to -1 times 1 plus cosine theta. So now if we try to directly evaluate from here by plugging in 0, the cosine of 0 is 1, 1 plus 1 is 2, 2 times -1 is -2. E. Okay. Jump to 7. Thoughts on 7? Say it again. Oh, back up here. How did we get -2? Plugging in at 0. Okay. Thoughts on number 7? Anybody willing to take a stab at it? What if I offered you bonus points? Oh, there are the hands, David. And what's your goal there? To get sine of x over x? Okay, so if I multiplied by x over x, this would have a limit of 1. So that would cancel. But still, when I go to evaluate, I'm going to have 0 over 0. Does that make sense, David? It's not a bad thought, but when you do it, it doesn't really simplify the problem. The problem is this cosine of x minus 1, because when I plug in 0, I'm getting 0 in the denominator. Rachel? So she's splitting it up like keeping the x over the cosine x minus 1 times the sine of x. What does that do for you? No. That only works if the cosine x minus 1 is on the numerator. That rule that we learned, that limit that we learned on Friday, only works if that was in the numerator. What'd you say? That was the reason behind not being able to use the reciprocal. But we still have 0 over 0. It's not like it's a number over 0, which would be undefined. It's still 0 over 0. Will? Sine x over sine x? Okay. Which would make x sine squared x over sine x times cosine x minus 1. Then what would you do from there? Into one minus. Oh, are you factoring it on top of it? So Pythagorean identity and then factoring 1 plus cosine x, 1 minus cosine x. Okay. Oops. These again are -1. Okay. Can. Because your sine of x is a problem, but with x over sine x, that has a limit of 1. So then you're just left with 1 plus cosine x times a -1 up top. So now we can reevaluate. We have nothing on the denominator causing an issue. So we plug in 0. 1 plus cosine of 0 is 1 plus 1 is 2. Times -1 is -2. No.
What?
Because I never said that I would give you bonus points. I said, what if I offered bonus points? Would I get more? I was thinking, would I get more people to raise their hands? And immediately hands went up, so no one really answered my question verbally, but I gotta. How about, does anybody know anything else I could do that was like a technique we used during the Trig Identities chapter, Michael? Right, your conjugate stuff. That would have taken Will's method, and you'll see some of the same mechanics happening, but it is quicker, I guess. So I'm not going to multiply out the numerator, but when you multiply out the denominator, you get cosine squared x minus 1, which is the same thing as negative sine squared x. So again, it uses that identity. And negative sine squared x, the sine x over one of the sine x's will cancel. And then the x over sine x has a limit of 1. And so again, you have a negative cosine x plus 1, which also gives you -2. So the denominator was sine squared, you with me? Which is the same thing as sine x times sine x. So this sine x cancels with one of those. And then the limit, this is one of our shortcuts, or our known limits from Friday that really helps us with trig. X over sine x has a limit of 1 as x is approaching 0. So I'm not going to say that they cancel, but it kind of looks like they do. But it's really because there's a limit of 1. Anything else on that one? Okay, jump to 10. What do we think about 10? Anything at all that you could try. No, you're on 11. Yep. Yep. So distribute the sign. You can only distribute numbers. Sign by itself is a functionality, it's not a number. So you can't distribute sign. But we're getting closer. Brianna? No. I would thought for a second you were going to try to distribute again, but no, you might be doing something else. What if I showed you this? X over sine x. What could I use here for number 10? The sum formula for sine of alpha plus beta. Because that's what we have here, sine of something plus something. So the formula says sine of alpha, which is pi over 2, cosine of beta, which is theta, plus cosine of pi over 2 sine of theta minus the 1 all over theta. And so because that 1 is pi over 2, some of this we can evaluate. What's the sine of pi over 2? 1. 1 times cosine is still cosine. What's the cosine of pi over 2? 0. So 0 times sine cancels. Minus 1 all over theta. So what's the limit of that as theta approaches 0? That's one of our shortcuts and limits that we have to memorize from Thursday. The limit of that is 0. Good? Number 11, thoughts. I think immediately when I see the limit as x approaches 0 from the right, I'm wondering why do they need to say from the right? Because it's an asymptote? Because it's an endpoint? Yes. Because you can't approach 0 from the left because the function doesn't exist to the left of 0. Those will provide all undefined values. But we can approach 0 from the right, and we're trying to figure out where that limit is. So, Brandon, what do you think? Okay, so he's going to go root x times root x because that makes the denominator x, right? So he's rationalized it. And so we have the sine x over x, which is one of our shortcuts because our limit of that as we approach 0 is just 1. And then we can just plug in 0. And the square root of 0 is 0. This might be a graph just worth looking at just because it's going to be window, yeah, sure. All right, there's that graph. So clearly you can see it doesn't approach 0 from the left. And it actually doesn't really look like the answer is 0, does it? Kind of looks like it's up here maybe a little bit. This is 0, 1, and 2. Kind of looks more like it's like 0.4 or something. But if we do second trace value and plug in 0.00001, we get a teeny tiny scientific notation type number. And you can see where the cursor brought you, pretty much to 0, 0. All right, number 12. I have something new to teach you here, but I'm going to wait till it comes up. So, thoughts on 12. The limit as theta is approaching negative infinity. What do you think, Dakota? Okay. What sorts of brainstorming things could you try? What'd you say? It's going to be the cosine of a tiny negative number. So he's this, I think are you plugging in negative infinity? Yeah, so he's kind of plugging in negative infinity. So when he does that, there's a negative infinity out in front. And then he's saying that 1 over negative infinity is going to be a teeny tiny negative number that's pretty much 0, right? And what's the cosine of 0? 1. minus the 1 is negative infinity times 0, which you all think is 0, right? Because anything times 0 is 0. Because this never actually gets to 0, 0 times infinity, if it was 0 times a whole number, then you could say that. Even though it never gets to 0, it's essentially going to be 0 and being multiplied by 5. When you keep multiplying 5 by a smaller and smaller number that's getting closer and closer to 0, it will also get closer and closer to 0. But this is negative infinity. And negative infinity times 0 or infinity times 0 is another version of indeterminate. So the only way we can do this is to either know what the graph looks like, which we have no clue, or to have a calculator at our fingertips. Okay? So if I type this in, x parentheses cosine 1 over x minus 1, and I want my window, I'll go negative 100 to 100. Oh boy, there's a little something in here. Maybe I'll go from negative 0.5 to 0.5. Okay, so it kind of looks like a rational graph, yes? But anyway, as x approaches negative infinity, what does this seem to be approaching? Because it kind of becomes one and the same with the x-axis, 0. Okay? Well, Mrs. Rahill, we were right. Anything times 0 is 0. It's not. That's just a coincidence that also ends up being 0. Because jump to number 29, which is going to be similar in the sense that we're looking for behavior as you approach infinity. If you plug in infinity here, you're going to get infinity times the sine of 1 over infinity, and 1 over infinity is also approaching 0, correct? So the sine of 0 is 0. So then that should also be 0, because 0 times infinity, Mrs. Rahill, is 0. Well, let me show you what this graph looks like. Sine 1 over x. Window, I'll do negative 100 to 100. I'm fine with that. Negative 2 to 2. Here's this graph. I'm going to change my window from negative to negative 10 to 10 so you can see a little bit more what happens around the y-axis. But regardless, as x is approaching infinity, this is 0, this is 1, this is 2. So what's the limit as x approaches infinity? 1. Which, how would you ever, it's clearly not 0. So that answer is 1. So 29, you'd only need a calculator. You'd have to have a calculator. And same thing with 12. But the takeaway from this is that 0 times infinity is indeterminate. So maybe in a case like that, there would be a way of manipulating it. But if not, we need a calculator. Okay? Who just had their hand up? I missed it. Calculator. But our typical indeterminate cases have been 0 over 0. So there's a new type of indeterminate. Has infinity times 0 come up anyplace else yet this year? I was trying to think back. Does that come up? I didn't think so either. It would have to be in a case where we plugged in infinity and thought about behaviors, but I don't think so. All right, so we'll be on the lookout for those if they come up. Jump to 22. Thoughts? Yep. Plug in 0, you get 0 over 0. So what? Done? Correct. Binomials divided by monomials are nice because we can split it up into two separate fractions. And then based on our limit properties, we can take the limit of the first part and add it to the limit of the second part. So that would be the limit. 3x over x is just 3. Plus the limit of the sine of 2x over x. So this is the only one that really needs manipulation. We can just give this a 2 over 2. And then the sine of 2x over 2x has a limit of 1 as x approaches 0. So we end up with the limit as x approaches 0 for 3, plus the limit as x approaches 0 of 2. And those are both constant functions, so just 3 plus 2. Limit of 3, limit of 2, so the overall limit is 5. I only like to prove to myself on the calculator that we're right, because it makes me feel good. And I'm always curious what the function looks like. So there's this crazy function. And it looks like it's, I went negative 7 to 7. I went, this is from 0 all the way up to 7. So when you look at it, you can see that as this approaches 0, clearly the limit exists. There obviously must be a hole there, but the value is 5. I could second trace and look for the value at 0.000001. Oh boy, I hit a bad button. And I get 5. And it brings me right to pretty much where that hole is. Okay? Jump discontinuity. So just to kind of review, a jump discontinuity comes up in what I think are only 3 cases that we've looked at. Number 1 are piecewise functions. If you've got one piece and then another piece, that's a jump discontinuity. Another kind of place where we have jump discontinuities are in our absolute value parent graph situation. Jump functions is what we call them. Jump functions, and we'll do more to review those tomorrow. But that was our absolute value of x over x type functions. That's a jump discontinuity. And then step functions, which we've seen a little bit more of over the last week. So jump discontinuities are non-removable, because in order to be removable, it would mean that you could take and place just one point on the graphs of any of these, and it would just fix the discontinuity problem. And if I just were looking at this piecewise, just putting one point somewhere is not going to fix my discontinuity problem. In fact, the only cases that are removable are holes. That's removable because if I want to place, if I get the freedom to place one point on the graph, and I can, if I choose wisely, I can plug it into a place that would fix the discontinuity issues. So holes are removable discontinuities. Jump discontinuities are non-removable. Is that fair? Okay. So of these functions here, which of these have jumps? Now, they're looking specifically for a jump at 0. This one has a limit at 0. What's the limit as you approach 0? 1. it also may help for you just to remember what this graph looks like. There's just a hole right there. So that is not considered a jump discontinuity. That's a hole discontinuity. So that's out. This is our jump function parent graph. So this is this guy right here. So that one does have a jump at 0. And what is 3? Once you simplify it, 1 over x, rational graph. That's not a jump discontinuity. That's an asymptote discontinuity. Okay? So that wouldn't apply as a jump. So the answer here is only 2. (24) gives us this function that we familiarized ourselves with on Thursday, and I'll tell you again, looks something like this with a hole at 0. And that function by itself is discontinuous. But they're making it a part of a piecewise function and saying what value of b would turn this into a continuous function. In other words, we need to plug this hole up. 0, 0. So b would just need to be 0. Okay, 25, which of the following functions are continuous? Again, this on its own is not continuous at 0. But they're making it a part of a piecewise function so that they plug up that hole with 0, 1. So is this overall piecewise function continuous? Yes, they plugged up the hole. In number 2, this is a jump function of sorts. It's not as straightforward as our parent graph. But sine of x over x, if I were to write that without the absolute value signs, approaches 1. So if you're coming from the right of 0, where x is positive, it's going to have a limit of 1. If you're coming from the left of 0, where x is a negative number, your numerator is going to be negative, but your denominator is going to be positive, so that's going to be negative 1. So this is, with those absolute values involved, it is a jump function, but I also want to show you what this looks like. All right, let me just get rid of my negative 10 to 10. Negative 7 will go negative 2 to 2. So like I said before, to the right of 0, it looks just like sine of x over x. But the absolute value getting thrown in there changes its values only for the negative side of things, and it really flipped it upside down on the left of 0. So we still have that jump at 0. So this is, they did give us another point, 0, 1, which is here, but they didn't plug up any hole. This was a non-removable discontinuity with that jump in there. So just throwing out an extra point in there isn't plugging up any hole, and so it is discontinuous. And then on number 3, 1 minus cosine squared, going back to our identities, 1 minus cosine squared is the same as sine squared. And what's the square root of sine squared x? Absolute value of sine x. Good. Right? Square root of something squared is the absolute value. Now this is a standard jump function. This always equals 1 or negative 1 because it's something divided by itself. It's just give or take the plus or minus. This one's actually interesting. Let me show you this one. Sine of x over I'm going to do this from negative 10 to 10. No, negative 10 pi to 10 pi. And I'm going to count by pi's. So we're up here, we're down here. We're up here at 1, negative 1. 1, negative 1 as we move across the graph. Why is that? Why does it keep going back and forth? What if I just do it from negative 2 pi to 2 pi? Maybe that would help better. So from negative 2 pi to negative 1 pi, it's 1. From negative 1 pi to 0, it's negative 1. John. Right. So if you're at if we kind of look first from 0 to 2 pi and go around the circle this way, from 0 to pi, sine of x is always positive. So it remains positive over positive, which is positive 1. When you get down in past pi, between pi and 2 pi, your sign is negative, so it's a negative over a positive, because the denominator is always positive. So the numerator oscillates back and forth every pi units. It's positive, it's negative. The numerator is positive, the numerator is negative. The numerator is positive, the numerator is negative. So because that kind of goes back and forth, at the same interval that this goes back and forth, which is every pi units, we go back and forth between positive 1 and negative 1. Do you see that? Okay, good. So at any rate, these are, well, this one is clearly a jump function as well. When that absolute value is involved, the jump function is at play. So the only one that is continuous is option 1. Okay? Good, 32. The last one. 32 wants our limit as we approach 0 from the left. Now, this is not the same function as the one that we know about, but it's pretty close, right? And we kind of just saw it, right? The absolute value doesn't do anything to the graph if x is positive already, which means if our graph looks like this side is still going to look like this. The absolute value is not going to change anything. But when we plug in a negative x value, our numerator is going to be negative initially, and our denominator is going to be positive. So it's going to flip this kind of upside down. So what is our limit as we approach 0 from the left? Negative 1. Good. Absolute values do funny things. Okay, so your homework is just going to be to finish this packet. You do that? See if you come across any other kinks, questions, and we'll finalize our trig studies tomorrow.